The aim of this lab was to successfully hit a target at a specified distance using a LEGO dart launcher by applying our knowledge of projectile motion equations to construct an accurate dart firing mechanism. Each group was supplied with a dart and a dart launcher, as well as given access to a crate of many different LEGO pieces. There were some initial struggles to figure out how we were going to apply projectile motion equations to design an accurate projectile launcher that could be altered to reach any horizontal distance within its range. Initially, we thought the equation r equals vxt would be useful as it provides horizontal displacement. We then applied the equation vy equals ui plus at to the first equation in order to get rid of the variable t. This did not produce the desired result, as we were still left with too many unknowns of vx, vy, and ui to form an expression to relate range with a specific launch angle. Eventually, we came to realize that vx equals v cos theta, vy initial equals v sin theta, and vy final equals negative v sin theta, as simple projectile motion states that the initial velocity equals the final velocity when the projectile is at the same y coordinate. This highlights the symmetry of the parabolic path of the projectile motion. So then, we use the equations r equals v cos theta times time and negative v sin theta equals v sin theta plus gt to form our main expression. We rearrange the equation 2 for t and then substituted for t in the first equation to form r equals negative 2v squared times sine theta cos theta all on g. From known trig identities, 2 sine theta cos theta equals sine 2 theta. This gives us r equals negative v squared sine 2 theta all on g. Now, we had to use this expression to relate launch angle to horizontal displacement. So rearrange to form the expression inverse sine of rg on negative v squared all on 2 equals theta. However, to further use this equation to map the motion of our dart, we have to find the initial velocity of our dart as it leaves the launcher. To do this, we use the fact that when firing a projectile vertically, at the vertex of motion, the point where the projectile reaches its greatest height before it begins to descend, the velocity is 0. So, we use the equation v final equals v initial plus at and set up an experiment to find the time taken to reach a point where v equals 0. As seen in the footage, we used a stopwatch, the LEGO dart launcher, and slow motion recording to find the time. After 3 trials, we averaged the time taken to reach the vertex and solved for the initial velocity, knowing that a equals negative 9.8 meters per second squared. From calculations, the initial velocity of the dart is approximately 4.41 meters per second. Since we now knew the value of g, v, and r, it was time to use our expression to find an angle that would reach and hit a target that was at a distance of 1.75 meters from our mechanism. As seen in the image, the mechanism was constructed using 8 LEGO arms and 4 pivot bolts. This allowed us to change the firing angle using protractor and to steadily attach the launcher to the moving arms. The launch angle was calculated using theta equals inverse sine of 1.75 times negative 9.8 over negative 4.41 squared, all on 2. Thus, our required launch angle was 30.9 degrees from the horizontal, or 30.9 degrees from the vertical. Observations. We noted that the path of the dart produces a symmetrical parabola where the initial velocity is equal in magnitude yet opposite in sign to the final velocity at the same y coordinate. Moreover, the main observation was that with regards to the expression, when range increases, the firing angle increases and vice versa. However, when using angles from the vertical, the higher path of parabolic motion, a greater horizontal displacement means a decrease in the launch angle and vice versa. Finally, we observed that the values within the inverse sine were restricted to the domain 0 to 2, meaning the dart could not reach beyond 2 meters or travel backwards. Within the initial velocity trials, the range of uncertainty for the dart's time to reach its vertex was 0.04 seconds. This produced a variation of 0.4 for its initial velocity when carried forward into the equation, which resulted in a launch angle of maximum 34 degrees and a minimum of 26 degrees. Thus, the uncertainty of the launch angle to reach 1.75 meters is 31 degrees plus or minus 4 degrees. In conclusion, after initial methodology struggles, our group managed to form an expression that links range with launch angle using the principles of projectile motion. Also, we were able to create a mechanism that relates the equation with experimental reality to accurately fire a projectile to a specified distance.